going to discuss how you can derive the laws of optics from electromagnetic waves and reflection and refraction at interfaces between air and a dielectric. So in a dielectric, it's easy to show that the dispersion relation can be written as k squared, that's the wave vector squared, is epsilon r omega squared over c squared, which tells us that the phase velocity, which is of course omega over k, is equal to c divided by the square root of epsilon r, and we often write this in optics as c over n, where little n is known as the refractive index, and this characterizes the behavior of light in the material. We've assumed here implicitly that mu r is equal to 1, which is almost always a good approximation, and particularly within dielectrics. So now we're going to think about what happens when we have light incident on an interface between two dielectric media. In terms of optics, that tends to be between air and something like glass. So it's a general kind of situation, but we're going to be thinking very much of the air-glass situation. So we have an interface here, and we have two refractive indices, n and n prime. Of course, that will also imply we have two dielectric constants, or two permittivities, epsilon 1 and epsilon 2. I'm going to make the interface lie along the x-axis. Of course, it's a plane, so it's lying in the xy plane. We can define a normal to the interface, and I'm going to say that that's along the z-axis. This identification of directions is not removing any generality at all. And we're going to assume that we've got an incoming wave. That's not a very straight wave. Let me draw that again. You have an incoming wave here with wave vector k, and an incident angle, that's an angle defined relative to the normal of alpha. We'd assume we have an outgoing wave, a reflected wave, with wave vector k double prime and angle alpha double prime. We do, of course, know from optics already that k double prime and alpha double prime are going to be the same as k and alpha. Of course, the direction of k double prime is different, but we're going to derive that. And then we're going to have our refracted ray k prime and the angle alpha prime. If we are being completely general, we would assume that the electric fields, those three waves, are as follows. So E is equal to E0 e to the I k dot r minus omega t. E prime, that's the refracted ray, is E0 prime e to the I k prime dot r minus omega t, and E double prime is equal to E0 double prime e to the I k double prime dot r minus omega t. Now, we've made an assumption already, which is that there are common frequencies, common omegas. And this is the correct assumption. We're thinking about waves, and this is a generic property of waves. They are driven oscillations, and driven oscillations always have the same frequency. We'll see in a moment a reason why this might also be applied. So we've got those three general waves. We are, of course, going to deduce various properties of k and k prime and k double prime. What we can say is that at the interface, we have to have certain conditions on the fields. Boundary conditions apply. Oops, that's gone slightly wrong there. Let me start that again. Boundary conditions apply. And what we can say is as follows. First of all, we can say that E plus E double prime, the components parallel to the interface, must equal E prime parallel to the interface. And we can also say, though we're not going to use this, that epsilon 1 of E plus E double prime dot n must equal epsilon 2 E prime dot n. These are the boundary conditions on the electric field that you can derive from Maxwell's equations. And what we're doing is we're taking the fields on the incident side of the interface, that's E plus E double prime, and we're making them equal to the fields on the other side, the refracted index, E prime, and applying an appropriate condition. So just by looking at these boundary conditions and the general forms of these waves, we must say that at the interface, and let's specify that at the interface, the position vector r is going to equal some point d, which lies in the interface. So at the interface, the phases must match. That's because there's no other way to ensure that the boundary conditions can be applied. There's no way in general for every point on the interface and at every time to arrange that unless the phases match. Now if the phases match, then we can write the following. We can say that k dot d minus omega t must equal k prime dot d minus omega t must equal k double prime dot d minus omega t. And you can see here perhaps a justification for why you might agree that the frequencies should all be the same, the angular frequencies should be all the same. If we were to pick a particular point in space, there would be no way to arrange to have all of the phases identical for all times unless the frequencies were identical. So that's the first thing that we've noted. We've got the same omega, and we've seen why that might happen for a couple of different reasons. Now let's think about the relationships between the vectors k. Since the angular frequencies must all match, we can then simplify this and say that k dot d must equal k prime dot d must equal k double prime dot d. Now let's specify this. I'm going to say that d will lie entirely in the xy plane, so it will have a dx and a dy component, but nothing in z. And I'm going to say that the incident wave k will lie in the xz plane, so it'll be kx 0 kz. Again, we're not losing any generality here. Of course, this means that k prime is equal to, in general, k prime x, k prime y, k prime z, but in a moment we're going to see that we can make some deduction about exactly what plane that must lie in. K double prime has the same form in general. So if we now just expand this out, we would write the following. If we assume, sorry, I missed a step here. No, I haven't missed a step at all. We're going to carry on, I'm sorry. So kx dx, expanding out, must equal ky prime dx, no, not ky prime, I'm so sorry, kx prime dx plus ky prime dy, trying to make these much clearer that they're subscripts, must equal kx double prime dx plus ky double prime dy. So all we've done is evaluated the dot products. Now we want to choose a line where dx is equal to 0. So if dx is 0, dy can take on any value. That specifies a line in the plane. Along that line, the incident wave, the dot product, will give us 0, and therefore we must have the following. Must have ky prime is equal to ky double prime is equal to 0 in order to fulfill the fact that the phases match at any point in the interface. We've just chosen a particular point. And what this means, of course, is that k prime and k double prime are coplanar. And if you want to keep score, that's probably what you would call the first law of optics. We can go a little bit further. We can see, actually, just by looking at this, that kx must equal kx prime must equal kx double prime. Otherwise, again, if the phases don't match, we can deduce that by setting dy is equal to 0, but notice that dx is non-zero. And another way, of course, of writing that is as follows, is saying it must be k sine alpha is equal to k prime sine alpha prime is equal to k double prime sine alpha double prime. What can we do from here? Well, we've already said that from the phase velocity we can write k is equal to n omega over c. Now if we label these equations, let's say 1, 2 and 3, or these terms, then if we take the equality that 1 must equal 3, that will imply that k is equal to k double prime. That's because n is the same, and therefore alpha must equal alpha double prime. That is the second law of optics, if you like. That is that the angle of reflection is equal to the angle of incidence. And then finally, by equating 1 and 2, we can deduce the following. We can deduce that n sine alpha is equal to n prime sine alpha prime. And that is the third law of optics. It's often referred to as Snell's law, though it was known a long time before that. Certainly around about 1000 AD, Alhazen and others were looking at this kind of optical property and deducing these kinds of behaviours. So what we've done is we've deduced the basic laws of optics and very simple rules to do with waves just by considering phases and boundary conditions. In a further video I will extend this to look at the Fresnel relations, which tell us about how the amplitudes of the waves, so the E0s, relate to each other.